Howdy folks, how you doing today? Happy Thursday. Sorry again for the trouble with the link for lab. I had it apparently was buried in the announcements from like way back when, the like welcome to class thing, and I totally forgot it wasn't somewhere else accessible. So sorry if you were confused about that, and hopefully you got a chance to join in there if you wanted to be live and look at that lab. So we can talk more about that later if you folks want. We've got a couple things today. We got to talk about linked lists first, and I think we're good on the stacks, queues, and decks. All right, we finished that all up on Thursday. I've not got a chance to grade your Trek Wars project. I'm sorry, I'm far behind on this now and got sick again. So I'm dealing with this cold, and it's the cough has been real bad. So I failed the daily COVID screen. They're like, don't come to campus. And then I get all sorts of links for like, you should go get a test, go get a test, go to get a test. I'm like, I don't have time for this right now, but hopefully I'll be feeling better soon, and I can go find, probably tomorrow, I'll go find a rapid test I can go take. But it's all like sinus pressure, congestion, and drainage causing the cough. I don't think it's any of the COVID stuff, but what do I know? So I'll go work at that and hopefully find out soon. So I think by Wednesday afternoon, then I should know for sure if I'm good to come back for Thursday or not. So apologies for changing things up here. That recursion project is due Thursday, so we're going to go over to the solution to that on Thursday. I've had a couple questions on that. If you got any other questions, feel free to put them in chat or send me a message. Let me know what I can do to get you pointed in the right direction on this. We should be pretty good to go. So we've got the other quizzes loaded up here. Again, those are all due next week by 11:59 p.m., so you can get them in and done, and I can score them for you before you go do the midterm. Was the idea there, because we have all next week set aside for midterm. Hey KMP, good to see you. Because I wanted you to have enough time to work on that, and not. I just don't like timed exams, and that's not a good measure of really can you do something. So, but I have to have exams in the syllabus in here. So, no lab, no lecture Tuesday or Thursday next week. We'll have all that. Which is actually close to 5 hours, which is weird, but it's a 4-credit class worth the time to put into the midterm here, because it's like half the quiz style questions. Again, just trying to make life easier here on exams, and then 3 long answer style questions. And I'll show you last semester's or last year's midterm. I'll get that one posted for you today. Then we can go over and look at those and what those might look like for the long answer questions. Okay, so it was like a recursion question, it was a stacks and queues question, and then I think a classes and unit testing question, but I'll double check that. So we're going to talk about linked lists today. Fire up PyCharm here. Took more medicines. I was trying to avoid some of that, but it's not great, so pardon all the coughs. If I'm thinking of it, usually I can get that mute button so I'm not coughing your ears off here. We'll see how well that works. And then after the midterm, we've got nothing else due, so we can actually have a spring recess. Or like midwinter recess? I don't know why it's called spring. Dearborn calendar. Academic calendar. This is how often I search this. It's like a recommended search for me. I think they called it spring recess, is why I put that in, but that's silly. It's not spring. Winter... Yeah, spring recess. Why would we call it spring recess? That's just, it's nonsense. Nonsense, I tell you. We're still waiting on PyCharm here a second, and then that'll fire up. We can go from there. I think PyCharm's starting. Yeah, there it is. Still thinking. Oh. So linked lists are a very different way for us to store data, and a very different structure and format, and for reasons of performance. So the problem that we have with this array-based storage, or regular lists here, is that adding anything in the middle, or like near the beginning, or taking anything out of the middle or near the beginning is really slow, because n things need to shift back down. So we see that's the slowness here when we look at, average case for inserts not at the end and deletes not at the end. Anything at the end, perfect, that's fine, it's really quick, not a problem here. But anything in the middle or near the beginning was super slow, and we looked at that, kind of exploring some of those graphs in lab last week. It takes time for all those shifts to have to happen. So what the idea here with this linked storage is that we don't need to have a contiguous block of memory to store all of our data points. What we're going to do is a different format. Let me start a new project here. Come on, PyCharm, work with me here. Almost there. And what I don't know, a way of thinking about how this works is if each of you came into the classroom and I gave you a number, right? So the linked lists here. This idea, so if you each had a number as you came in, but what I would give you then is, instead of like telling you where to sit, I would just say, okay, here's the person that came in before you. Let me fire this up here. I can start sketching out in Word. So the idea with the linked list is that the particular piece of data knows what comes next, is our basic linked list. A singly linked list is what we're going to look at first, and then we'll get some more interesting ones after. All right. So if you start coming in, and I want to know like who came in what order. Sorry, imagine we had our little Y page setup. That's not what I pressed. Right, had a bunch of desks here, and you don't have to sit in any particular order. You can sit anywhere you want, right? In this particular layout, we'll put a bunch of desks around here, right? And I want to know the order in which people came in, but I don't want to have to like put you in a certain thing here. So what I'm going to do is I'm going to say, okay, let's have. We'll say Bob came in first, and Bob sits up here, right? And then who comes in next? Well, maybe Mary comes in next. Mary comes in, sits over here. I'm going to say, hey, Bob, you come before Mary. So Bob will point at Mary here. We'll say, okay, Mary comes after me. And then someone else comes in, and maybe we have Sue over here. Terrible with creative names, I'm sorry. And I tell Mary, hey, Mary, Sue came after you. You point at Mary here, or you point at Sue. And then Tim comes in, and Tim sits over here. I say, okay, Sue, Tim came after you, you point at him. And we just follow this chain of these links here. And I can say, okay, I don't know who the fourth person is. I can't get to the fourth person directly. But I can say, okay, Bob, you're first. Who comes next? That's Mary. Mary, who comes next? Sue. Okay, who comes next? Tim. Tim comes next. Tim, who's after you? And Tim says, nobody came after me. So we're done. So a lot of times what we'll do is we'll visualize this as a node here. We'll say this is a node. And the node has some data, and it has a next. So the node will point to the next node in this linked list here. Data and next. Right. And it can point to the next one, and point to the next one, and point to the next one. Excuse me. So we can build out this basic structure here. So I'm going to write a class for, let me zoom this in a little bit. For linked list. And then it's actually going to have its own inner class here, like a private inner class. It's just belongs as part of this class for node. And then node then has an init method, given self and some data. And I'm going to say next, and we're going to assume it's none until I know otherwise. So I'll say your next is none. So then self.data is the data, and self.next is the next. Now, I'm not going to mark any of these as private or anything, because I'm using it directly internally as part of linked list here. So then linked list here will define a init method. Now, I'm just going to start off as an empty list. Right? We don't have a way of adding things to us right now. But what the linked list has is it has a self.first. That'll be private here. First is going to be a node. And it has none right now. Actually, it can be none, I guess. We can do that. We can have nothing. We just don't have a first. Right? There is nothing first. That's fine. And then we can go and we can say, hey, if you want to add something here, you want to add some data here, I'm going to say, hey, if my self.first is none, then self.first is a new node, given the data, right? Is it self.node? No, linked list.node, I think. It's a little bit obnoxious to have this inner class, sorry. So it's a new node, given that data, right? Then what I can do is I can say, hey, if I want to otherwise, right? So this otherwise, sorry. If it's not none, what I can do is I can say self.first is a new node, linked list.node, given the data, and then what comes after this one now is the old self.first node. So as I start adding things, this is going to add it more of like a stack style, where every new node then becomes the new front, the new first node. Right, so here's my linked list. If I don't have a value, now I have first. First has some data, and it has, for its next is none. There's nothing here. Let's put like a slash. If I add a new one, then I say, okay, here's a new node. So here's some data. And your next now is this guy. And now this is now the new first. So then I can add another thing. We'll add another node over here. This is now the new first. It has some data. What comes after it is this one. So we're always adding to the front here. We'll look at some other ways as we go, but this is like the basic one here. It adds it. So then if I want to get the value out here, so we'll define, how about pop maybe? I want to pop a value off. You can imagine this kind of like a stack here. We'll say if self.first is none, we're going to raise that error here. It's no good. Oops. It's none. We're going to raise an index error or something like that. Sure. Otherwise, what we're going to do to take the first off, I'm going to say the data is self.first.data, because I'm going to have to return that data element. And I'm going to say my first now. So to remove the first one, right? If I want to remove this first element here, what I need to do is I need this data to come back out, and then first needs to change to this one. Well, first is the old first's next. So you can say, okay, sure. So my first becomes self.first's next. So whatever came after first is now the new first. And then we can return data. If what comes after it is none, then the next time it'll be none. So we can define an isEmpty. We're going to return self first is none. If our first is none, we are empty true. If it's not none, empty false. Now we don't have a way of counting length. We can have a length if we want. Every time we add something, we can increase length. Every time we pop something off, we can remove from that. So we can do that. Self dot number of items maybe. Start off at 0. And every time we go add something here, we'll say, oops, sorry, this should be an else here. So only if it's not here. Right? We get a new first or first moves here. then we'll say my number of items goes up by 1. Plus equals 1. When we pop something off, we can take that down by 1. So then I guess we could just compare that to 0, right? Maybe that's easier. And then we can define a length method here, right? We're just going to return the number of items. We'll tell you how many items we have. And then we could add a peek method, right? We can define peek given self, return self.front first data. Right? And you probably, again, do this index error otherwise, because if we're empty, there's nothing to peek at, and it's just going to crash. So, and we can show you the first data. So right now, with a linked-based storage here, then, we can make a quick little stack out of it. So we can say, hey, my linked list equals a linked list. And then for number in range, let's do 10. Let's take our linked list, and then we'll add the number. And then while my linked list is empty, right, not is empty, we're going to print my linked list pop. Again, not very interesting, but we should get a stack behavior out of this. Right, we give this a run. We should get 9 through 0 back out, because we're always adding to the front. So what's really cool with this, though, remember when we talked about performance, we said generally we care about average case, right? Worst case is important, because sometimes you'll get that worst case and it'll be super slow, but often we don't really care about best case, because really you're not going to get the best case very often. But what's really cool with the linked list is that the worst case performance for adding something is still constant time. No matter how many items we have in here, it still takes just this couple, like 3 operations here to add a new item. There is never any resizing that has to happen, because we don't have a contiguous block of memory. So this is actually a more efficient data structure for us in terms of time. So this is O of 1 always here. Right? It's a constant operation. There never is resizing, like an array-based list. So that's the beauty of that. And again, the peek and pop, we were able to get O of 1 on those as well, right? But O of 1 for peek in our array-based lists, O of 1 for pop as well, right? Because we were just taking the last thing off of a Python list. So peek was fine, pop was fine. Eventually, this did lead to the list being too large, but we didn't care too much about that. In terms of memory usage, it wasn't too bad here. But by using this linked storage where every node points to the next node, it's super handy. Right? Now, what if we want it to be like a queue, though? Right, where we could enqueue and dequeue something. So the first thing in is the first thing out, instead of this stack-based structure. Well, we can do that. So this is, how about a linked list? Well, let me rename this to stack here, and I'll change that. Because we're going to be very similar here with a queue. But what we need to do, linked list stacked.node. For a queue, then, we need to take from the front, but we need to add to the back. So we can do that. So I'm just going to copy paste, if you don't mind. The book goes through like all this weird inheritance stuff, and I think it's easier to just have standalone classes, if that's okay with you. So a linked list queue then has a self.back is none. So when we're adding items, let's call this, how about enqueue? I guess we should have called it push, right? If we're doing that. So this is push. You push something on the stack, right? Let's do better about this. So that was our push. There we go. Push and pop. All right. So with our linked list queue then, you're always going to be adding to the back, but taking from the front. Okay, so that's not so bad. So if the first is none, we don't have anything, then we have a new item here, and then self.back is also self.first. Oops, oh goodness, that was too much. Self, there we go. So the back and the front are the same item here, right? Otherwise, so this now needs to change here because I need to add something to the back. So what I'm going to do is I'm going to say, hey, self.back next equals a linked list queue.node. There we go. I'm going to rename this one here. Linked list queue dot node given the data. So I can add something at the back if I know where the back is. Right? If I'm tracking where the last item is in the queue, I can add something after it by setting it next to something. And that it's going to be a new node of data. All right, on my items here. So my unique case here then is first becomes first and back when we're empty. Otherwise, back is here. Right? And then we pop something off. We're still taking it off the front. Right? The front stays where it is. It moves and moves and moves and moves. Right? The problem that we have here, though, is if I take off the last item, back needs to go away. Right? So if I add a bunch of items here, let's just put it on the page, I guess. So if I add 3 items, right? I say, okay, let's add, and we're always adding to the back. So first item we'll add as a 3, and then it has no next, and we add another item. Let's add a 4. We'll add it to the back. So now it has a next here. 4 has no next, and then we'll add a 5. We'll say, okay, you now have a 5 here. 5 has no next. And then I take 3 off, right? So this is my front, or first. Is it front and back? Did I do front and back? Did I have first and last? I forget. I have first and back. Okay, it should be like front and back. There we go. Let me fix that, because that's going to be annoying. Let's rename this here. So refactor rename to front. There. That'll make life a little easier for us. So that's the front item here. I think first is okay for stack. That's probably fine. We want it to be called front here for our structure. So first, if I take the first off, great, no problem. First becomes first next. Okay, first next, easy, done. Okay, now take this one off again, pop another one off. First becomes this one. Now this is also back, right? When I pop this one off, now first becomes this last here, but back still looks at something. So we need to say, hey, if first is none, back also needs to be none. Because otherwise when we try and add something, we're going to add it to this one here, and it's not going to update properly. So it's a little bit funky. So when we go, this is DQ, right? DQ, and this is front. So NQ then, so that's fine. DQing, that we need to be careful. So if now self.front is none, self.back also needs to be none. Right, so this is only if we removed the last item. Keep back from pointing at it. Messing up add. So I mean, it should be fine here. Oh yeah, you can just say if. So this is like a little Python syntax here. You can just replace it and say, oh, is none. Yeah, is none. Sure. So if it is none instead of equals none, it's probably better here. Sorry. Did we do that anywhere else? I don't think we did that anywhere else. Oh, we did. Okay, we fixed it for the other ones. So if it is none, there, we need to go and remove it, because once front becomes none, I guess our NQ is probably fine. If front is none, it sets front and back. But if we still have back pointing or referencing some value, it can't get garbage collected. So this is important for the garbage collection process, that if back is still looking at a variable and everything else doesn't need it anymore, Python won't give it away, won't let the operating system have the memory back, because it still thinks something's referencing it. This is for, this is, I guess, for garbage collection, from being garbage collected and freeing the memory. That's kind of a long comment there, sorry. How about bump this down? There we go. Is that a little nicer maybe? So you can see all on one line. So we should be able to do this with a queue then. Oops, let's back a line. There we go. So this is our linked list queue. So that's NQ, right? And that is DQ, right? DQ. So we should be able to get the numbers in order now. So we'll get them reversed from the stack, and then in order. Uh-oh, index error. What's up with our is empty? We weren't taking number of items down. We broke something. Where do we break it here? DQ. Front is none. Okay, well that's interesting. Oh, that's the... No, do we do it right? Linked list queue, that is all of those, is empty. Number of items is 0. Yeah. Adds 1, starts at 0. All right, so we messed something up here then. So when we DQ something, take from the front. Front goes to front next. Number of items goes down by 1. For none. Wow, what did we do? So we got... Uh-oh. We got 0 and 9. Okay, so we're really messing something up here then if our NQ isn't adding these right. So NQ says, okay, if our front is none, add a new front. Otherwise, the back's next is a new node. Should be fine. Let's run in the debug mode. So something is weird happening here. Let's put a breakpoint in here and do debug. Give this a second. Excuse me. All right, so here's our linked list queue. Then we can see we have a front and a back. They're both none. Okay, that's fine. We should be about to NQ number of 0. So let's do a step into, and we'll see. Okay, we're going to NQ if front is none. Let's make a new front given the data. Make that. Yep, we got a new front, and now back will equal front. Number of items goes up by 1. And our linked list queue then should have number of items is 1. It has a front and a back. Notice they're the same location here. Right, same data, same next. Right, no problem here. So let's do a step again. So let's step into. Now number is going to be 1. Right, so now the value of number is 1. Let's step into our code and watch this happen. So front is not none. So we're going to say back's next is a new node given the data. New node given the data. Number of items goes up by 1. So let's take a look at our linked list queue then. There we go. So back and front didn't change. Front has a next now. Next value is 1. That has none. Back. Oh, we didn't update back. That's the problem. So back needs to become the new back. That's what we missed here. So after we add something here, right, then self.back needs to become the new back. Self.back. .next. The next thing is the new back node here. There we go. That was going on here. Because back needs to be the thing at the back. All right, let's give that a run. It's totally on purpose so you can see how to use the debugger again. All right, and there we go. Now we get our numbers in order, like a queue. Again, it's always O of 1 performance here when we NQ something. There's never any resizing on average or worst case. Right? There's never that worst case where we need to resize. So it's really efficient. Right? Works out pretty well. Does that part make sense? How we can get this sort of performance with these linked nodes here? Let's see, why is it not like that? One last line. There, okay. Too many new lines here. I like when those yellow lines go away. Hey, Zenjamin. Thanks for hopping along. Following along. I'm not doing well. I'm on cold medicine. I tried not to, but it was too much. So I'm a little loopy. I apologize. It's a day. It is a day for sure. Oh, that's interesting. My camera is not mirrored. So this is my left hand. Usually, like, you get a mirror image on a camera. I just noticed that. That's one of those things. Oh my goodness. Sure. All right, cool. All right, so far, really good performance here for lists, for stacks and queues. But what if we want just it to be an actual list? right? To do all the things that a list can do, like to get a value out at a given index, or to insert a value at a given index. Now, I don't think we actually went through and did that with our array-based lists, because, you know, Python already had it done for us. But we could do that, right? So we're going to have another class here, then, for, this is a linked list. This is just a general linked list. Define in the init. Now, I'm going to start with the queue-based one, because I want to have the front and the back. And really, it's going to be sort of like a deck at this point, right? The DQ thing. Oops, that was wrong. Where you can add to the front or add to the back. Right, so we need a front, we need a back, we need an NQ. Or how about add front, maybe? This is add back. And how about we add an add front? Add front, given some data. Right, and that's basically the same thing we did with our stack. We add it to the front here. So our linked lists add back is fine, add front here then. We'll say, okay, if first is none, we have a new first, and then also then set back, right? Equals self.first. Great. Otherwise, first is a new node where the old first is the new first. Oh, that's right. We were doing front and back, so this is front. Front, 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 front. Okay, so we can add to the front. Right, this is still an O1 operation. Constant time. Right, we saw that. Front. Goodness, front, 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 front. Okay, we can add to the back, we can add to the front, we can get from the front. How about just get from the back? Define back. So if our, sure, I guess the same check here, not a problem here. If not, we'll return self.back.data. It could check back too. I guess it doesn't really matter, because they should be the same. If front is none, the whole thing's empty. And then DQ is, what is this? Remove front, right? Remove front. And then we could have a remove back as well. Now, remove back is problematic. Remove back. So the problem with remove back, right? So if we're going to have this list here, let me actually undo here. Let's redo some of these. Here we go. There we go. So we got our first, our front, right? This was our front. This was our back. Here, to take away from the back, I need to set this one's next to none. I have to get there, though. I don't know where this node is. I don't have a reference to the one before the back's next, right? I can't do that. So the slow operation then is we have to go find it. Right, so to remove from the back, we need to go find the node that is the last one. So the easy case, we can say, hey, if self front is equal to the self back, right? If we're that, right, then, hey, I'm just going to remove front because I already know how to do that. Return remove front. Right, that's already solved. That's the easy one. If we don't only have one item, I need to find the node that comes before the last one. So I'm going to say, hey, my current node is equal to self.front. And I'm going to do this little loop here. So I refer to this as walking. So we're going to look at all of these connections and walk the path here of this one to the next one, to the next one, to the next one, to the next one. We're going to walk along all those pointers and say, okay, what comes after you? What comes after you? What comes after you? So we're going to say, while current node next does not equal self.back. So if your next is not the back, then what do we need to do? Well, current node needs to become current node's next. Go to the next node. Go to the next node. So starting at the front node, go follow those trails. Okay, what comes after you? What comes after you? What comes after you? What comes after you? Until we find where, oh, back is next. Then once I'm there, I can have the data as the current node's next data. right? So the next thing is going to be the back. So I need to go get that data out. Then I can say self.back is equal to the current node. So it bumps it up by 1. I can return data. Oh, not yet, sorry. And then my current node dot next equals none, and then I can return the data. Right, so maybe do this first here. I don't know. Sure, why not? Doesn't really matter. So this is clears the link to the old back node for garbage collection, right? And then moves back 1 node, and then we can return that data. So the problem here then is this is always O of n, because I have to go find the second to last node all along this chain. So if I have 100 things, I have to go start at the beginning, go to the second thing, and the third thing, and the fourth thing. I have no way of jumping to a particular index. So linked lists are slow at getting to a particular place. Right? It's really slow here. Excuse me. But I can return the data. I can tell you if I'm empty. I can get the length. So I should be able to do all the same things out here now. With this is essentially the linked list. How about we'll call this the deck? Why not? Linked list deck. And then we go grab all these, change all these ones here. I have all those ones there. Sure, add to front, add to back. So let's go try it, right? So let's make a linked list deck. Here's a linked list deck. And then how about we add a couple to the front, add a couple to the back. So we'll say, I don't know, for a number in range, let's go 5 to 1. Let's take our linked list deck and let's add to the front the number. So it should add 5 and then 4 and then 3 and then 2 and then 1. So when we get them in order, then they should be in order. And then we'll go add some to the back. We'll say for number in range, let's go from like 6 to 10. Let's do that linked list deck, add to back, given the number. So we should get 0 through 9, again, in order, right? And then we can say, while our linked list deck, or not, our linked list deck is empty, do you want to get them in order or out of order? I mean, we could probably try both ways here. How about we take, we'll print the linked list deck dot remove from front. Let's do it one more time then. So we'll do just we'll repeat and see if we can remove from the back. Or no, let's do one each. Oh, why not? One each. We'll take from the front and the back. We'll just be crazy here. Remove from the front and remove from the back. Right, so we should get 0, 9, 1, 8, 7, 2, 7, right, on and on and on. I think that'll work because we're going to have an even number. It might be issue. It'll have an issue if it's an odd number, but it should be okay. Oh goodness, index error. Remove front. Uh-oh. We didn't check if front is none, so we should do the same thing for removing from the back. If back is none, we should give that error. Let's try it again. Okay, so we're getting there, right? We get, let's see, we get 1, 9, 2, 8, 3, 7. Oh, did we not get 0? Oh, I have an odd number. Yeah, because I went down to 0, but not including 0. Here we go. So if I go to -1, it'll stop at 0, and then this won't crash. We had an odd number. That was my mistake. Okay. Did it crash? Let me try it again. Oh, it does. All right, but we get 0, 9, we get 1, 8, we get 2, 7, 3, 6, 4, 5. And then where's it crashing here? At remove front. Oh, is empty? Oh, our remove back doesn't decrease our number of items. This number of items needs to go down by 1. Right. There we go. That ought to fix it. Okay, now no crashing. Hooray! Right, and again, we get them off in that weird paired order. But now we have the working deck, essentially, with this add to front, add to back. But this one's slow. Right? Our remove from back is slow. So can we do better? Sure, we can do better. We can definitely do better. Let's do this. Let me go copy our linked list deck here, and let's do one better. So I want this is called a doubly linked list here. The idea with a doubly linked list then is our nodes now have a next and a previous. So you can tell me what comes before you and what comes after you. So if I have now what comes before me, what comes after me, let me rewrite this here. So we'll say, hey, I'm going to start up a node here. So if I have a node here, it has a previous and it has a next. And we'll put a 3 in there. Sure. Now this is first. It's also last. Or back. Front and back, right? Front and back. Cool. Now let's go add another node. So let me add, I should have moved that up more over to the side. We'll add a 4 here. Let's add a 4. It's going to be the new last, so it won't have a next, but its previous then will be 3, and 3's next will be the 4. Its previous is still going to be nothing. If I want to add another node to the back, right? Let me add a 5. This one now has a next. It points to 5. 5's previous points back to 4, and it doesn't have a next. So now to change the last item, if I want to get rid of the back here, right, I can get at back by the back's previous instead of having to walk that current node thing. We just need to change a couple items here. So when you add to front, not a problem, right? You don't have a new, your next is self front, but you don't have a previous. When you add to the back, we're going to say your previous then here. So next is none, but previous is going to be the self.back, the old self.back. Oh, we got to change all these to the doubly linked. That's why. It doesn't know what that is because we're using the wrong node here. So I can say, okay, and this next is none as nicely as it defaults. I can say previous is self.back. So when you add to the back, I'm going to say, okay, your back now is this one. But then I need to go change. I'm sorry, no, back's next we did. Yep, and we set our previous to there. So we should be good. So now the operation for adding to, or I'm sorry, removing from the back. When we go remove from the back, I don't have to do this whole walking thing. None of this has to happen here because I can just say, again, if we only have one, sure, but if we don't, then I'm going to say the current node then is my back's previous. And I don't have to do any of this walking. And say, okay, go to what comes before the end, grab the data out, and really, this can just be self-back, really. I don't even need to do that. Self-back. .data. The current node next becomes none. Self-back becomes the current node. Take the number of items down by 1, and we're good here. So this now is O of 1, always, because I'm a doubly linked list. My nodes have both directions, front and back, for me to work with. So we should be able to swap that out here with our doubly linked deck and see if this works for us here instead of the singly linked deck. Everything else is the same here, right? We're just going to get better performance from removing front, removing back. Should still work. Okay, we still get our numbers paired off, 0, 9, 1, 1, 8, 2, 7, 3, 6, 4, 5. Looking good so far. So we didn't break anything, which is good. We can remove from back. And now it's performant, just by adding another link. Now, what's the trade-off, right? We said, okay, it performs better now with time complexity. By adding another memory reference here, we're increasing the amount of memory usage that we're using, because every link now needs to have another reference. So we've gained time performance in a trade for memory usage or space complexity, right? You have time complexity and you have space complexity. It sounds like, what is that, Doctor Who with time and space or something like that, but we're saying I can be fast now because I know where the back is. Does this make sense? We're coming at it kind of fast. We're going through, it's some interesting concepts here, but it gets to be a little interesting here. Now, this is a little bit obnoxious, though, with all the special cases here, and I find this annoying here. So there's one thing we can do better. We're still not a list yet, but one thing we can do better, and then we'll become a list. Okay? So let's take this here. I'm going to copy all of that. We'll do one more iteration here. We're going to call this a circular doubly linked deck, doubly linked list deck. I guess we're not even a list here. We should take list out of all of those. So the idea with a circular doubly linked list now is what I'm going to do is I'm going to start off with a dummy node here. It has no data. So this is my, I don't know, the head node or the start. I don't know. What do you want to call it? I'll call it the origin start. I don't know. How about start? We'll call it start. Its next is itself. Its previous is itself. And our list is empty if start's data is none. Or starts next is itself. We got a couple options here, but we've got this particular dummy node here. And this is going to make life a lot easier for us here. And you're going to see this, I promise. So when we make a new linked list here, then I don't need to track front and back. I'm going to have a self start is a new circularly doubly linked list node. We're going to replace all these here. We just keep getting longer and longer and longer names here, sorry. A new node, given none for the data. The other ones don't matter right now, but then I'm going to say self start previous is self start, and self dot start next is self dot start. Okay, so we're going to look at ourself. Now, what's nice about this is I don't need to check if front is none. Front is never going to be none, right? All I need to do is do this exact same operation now. Oops, let me tab that in right here. But it's not next now, it's the, so if we're adding to the back, we're starts previous. So starts previous, right, is always the last thing in the list. So we're going to say its previous now is self.start. And then what is its next? Well, its next then, we should do, I guess we should do next first, is going to be self.start.previous.next. I know that sounds ridiculous here. Previous.next. I think that's going to do it for us here. Oops, and we lost that previous. So we'll say, what comes, so if you're going to be the new end of the node, here, if we're going to add to the back, I'm sorry, so what comes after you then is self-start, sorry. What comes before you is self-starts previous. So whatever used to be the end is now your end, and what comes next is this start. So if we're going to add a new node here, so if we were to add a 3 with the new node here, right, we said, well, what comes after, so you are now, if we're adding to the back, right, regardless of if we're empty or not, you now are the last thing. So starts previous becomes a new node here. So we're no longer pointing here. Starts previous is now you because you're the back. Okay? Your next is start because that's the end of the line. Here we got to the end. So your next then is start here. And your previous is what used to be previous, which was this one. After we add you in then, we need to say, okay, we need to fix up our link here. So then our, here we should do this, sorry, as a new node. This will be better. This is a new node here. And we'll say new node dot next dot previous. What comes after you, before it, is you, is the new node. And then new node, what comes before you, after that, is you. It's going to be crazy here, but that's okay. I promise. I promise. So we'll set all this up. Let's try this one more time. So start, then its next is itself, its previous is itself. Points to itself. We're going to add a brand new node. This new node, when we're adding to the back, its next is start. So we say, okay, the next thing here is start, because you're the last thing. You get back to that start node. Its previous then is whatever start's previous is. The start's previous should always be the last thing. So what comes before you is also this thing. Okay? Then, hey, thing that comes after you, you come before it. Hey, thing that comes before you, you come after it. We're putting it into the correct location here. So my next's previous is now me, which is start. So I say I come before you. My previous next is now me. I come after you. Sounds crazy, but now let's add another thing here, right? Let's add a 4. This one, it hurts your head, but you have to think of it as a circle. And this dummy node, the start node here, is super helpful because it makes our code cleaner. So we'll say, okay, we're a new node. Your next is going to be start. Okay, sure. So next is start because we're adding to the back here. Next is start. Okay? Your previous, where did it go here? Your previous is whatever start's previous used to be, because start's previous was always the last thing. So previous here is this one. Okay? I added a new node, so I'm in the right location. Now I need to tell what comes after me that I come before it, and what comes before me that I come after it. So what comes after me? So what comes after me is my next. That's start. Say, hey, start, your previous now is not there. Your previous is now me. And hey, what comes before me? Your next is now me. So start points to the first thing. Its previous points to the last thing. And we have a nice chain here. So it's super pretty to do this here. And we don't have to worry about any of this back stuff here. Front and back. Now it's going to work essentially the same way here for add to front, except now when we're the front, our next is the start's next, and then our previous is just the start. Right? We put ourselves between start's next and start's previous. Right? So the front node, its previous is always the start, and then it's whatever came after it. And then we tell, hey, the thing that comes after me, put me here. Thing that comes before me, put me there. Now, you're going to think, oh, hey, this is the exact same code. It sure is. We can do better. Yes, we can. Right? We don't want to feel bad about ourselves, so let's write a method here. So let's, as a private method, add node, given the data, the next, and the previous. Right? So we can do this exact same thing here. But now our next then is just the next, and our previous is just the previous. So to add to the back then, we need to just call self.addNode, given the data. Now what comes after it? Well, that's the self.start, right? What comes before it? Self.start.previous, right? Your next thing is the start because you're the end, and what used to be the end is now before you. Okay, add to front, same thing here then. We can cut this down to a one-liner. But now what comes after you? Well, that starts next. What comes before you? That's just start. Okay. Now for our front and back here, we'll just check is empty. I think it's probably is easiest here. So if self.isEmpty is empty, we'll raise an index error. Otherwise, now it's always going to be starts next data for the front, and back, same idea here. But the back is always starts previous is data. Okay, so we're moving from the front and moving from the back now. We're going to be super easy as well. Okay, so again, we're just going to do the same. If we're empty, raise an error here. I think that makes life easy. Okay. Now, to remove from the front, right, that data is self.start.next. So really, let's make this a little easier here. So let's have the current node here. We'll say the current node is self.starts next. Right? So that's the first item here. Then we're going to take the data, is the current node's data. Okay? Then to take an item out of the list now, we need its previous to jump over it, and its next to jump over it. So I'm going to say, hey, 3, I need your next's previous to be your previous, and your previous next to be your next. Sounds crazy, but it doesn't. It doesn't. Okay? So we'll say data's next's previous. I'm sorry, current node's next's previous. So the thing that comes after you, what comes before it, is the current node's previous. Jump over me. And hey, thing that comes before me, previous, what comes after you is the current node's next. Right? We don't need to worry about any of this stuff here. We can just return the data. Right? So we're saying, take me out of the circle. Right? Thing that comes after me, what comes before you is what came before me. Thing that comes before me, what comes after you is what comes after me. Jump me out of the loop. Right? Take your before and after and make them jump over you. Right? Now removing from back is actually the same thing. Right? The same removing a node here is you just have to tell it which node. Right? So I'm going to take all of this code and we're going to cut it out here. We're going to have a define remove node given the node. So the node here then is the current node here. Great. Data's there. Take our items down and we'll return the data. So it can remove any node that we want by grabbing the data and making previous and next jump over it. So to remove front then, we can just return self.remove node of self.start.next. Right? Because starts next is always going to be the front. And then remove back then is super fast as well. Right? Instead of starts next, it'll be starts previous. So you can see how this makes this so much cleaner. Right? And we can even add this index error here. We'll just add it in this, right? When we remove a node. We don't even need to do the checking, right? Because we can do it in the helper method. Does that part make sense? So the back and front, right? Sure, we're checking. Looks good. Add to front, add to back. Easy. Now the circular doubly linked list is a little confusing, and we've gone over it kind of fast. So we're gonna spend some more time with it on Thursday after we solve the project. We'll look at using this now to become an actual list where we can add stuff at given indexes. We haven't got there yet. We had to set the stage, but you can see now our code is really easy. Right? For adding a node, we always do this thing. For removing a node, we always do this thing. Right? So let's see then if we can use instead of a doubly linked list, we want to use the circular doubly linked list for a linked list deck. See if that runs and no, it doesn't crash. Seems like we get everything out. So by having this little starter node or head node or dummy node, whatever you want to call it, because there's always a node, it's never none, it makes life so easy for us with this little start node. Because the code is always going to be the same. Right? It's just saying, okay, where do you go between? And then we'll fix it up. Or where do we take you out of? Well, okay, what comes before and after you then? We have to jump you out of the list. That make sense? All right. We'll launch GitHub here. We'll commit this. This is a good start. We'll pick it up from here on Thursday. Oh, I need to give you the midterm. I got to go grab it. Let me go grab that here real quick. Do another. Let me just throw it on my other screen real fast because I'll make sure I pull up the right thing here. I don't know what's going to show. Let me just go grab that real quick. 2001. All right, and this is look at the midterm preview. All right, this will be for 2001. Trying to preview it here. There it goes. It's just loading real slow. Oh goodness, it's shuffled. Oh, that's annoying. Let me do this here. Let me. Oh goodness, it's still loading. Here's lists. All right, so I can just add this. I don't know. Do you want to print it all? Yeah, probably fine. Oh, okay. Yeah, we used two-dimensional lists. So one of those things in recursion. Iterative functions. I'll just print it as a PDF. It's not going to be the prettiest PDF though. That's a little sad. Yeah, let me just grab the questions because it's going to be an ugly PDF. Is that okay? So I'm going to grab this tab, and then we'll come back to Canvas. Wow, it's running super slow. I'm sorry. Canvas. All right, so let's do a little practice here. I'll post them in here. So where do you want to? We'll just do a new. Do a new module, I guess. So this is midterm here. Bring that up. I don't want it to be stuck in there. Let's add a new file, a new page. Here we go, a page. Create a page, midterm review, or practice, I don't know, sample, maybe practice. Okay, we'll go edit this page. Okay. All right, so this will be untimed, open book, open notes, open internet. It'll be 15 quiz style questions, like literally from the same test bank here. And then it'll be 3 long answer coding questions. Okay, so some example questions that here's like one on, excuse me. So given the following UML, write the class. So here's pizza is the name of the class. Here's our attributes, and then here's our methods, our functions, right? And then we'll also then write a unit test for get total price. So the class, right? Here's the UML, and then write the unit test and the class for it. Okay, that's one. So one classes and unit test question. One 2D list question. Can I bump that? There we go. Something like this one here. Let me see if I bold this. Let's do a little header. There we go. Clean this up. Okay, so write a function sum of values and even product of indexes given some list returns the sum of all values and indexes whose product of row and column index is even. So if I were to give you this list, the row and column indexes would be 0, 0, 0, 1, 0, 2, 0, 3, right, on and on and on. The ones that have an even product then, I've bolded 1, 2, 2, 1, 2, 2, and 2, 3. Is 0 even? I guess 0 is probably even, right? I guess 0 is even. We should bold that one. So 7 and then 1, 1 and 2, right? 0, 0? Is 0 even? Yeah, I guess 0 is even. Ugh, is that really all the first rows? right, math friends, is 0 even? I don't think 0 is 0. All right, let's Google it. Is 0 even? Consult the almighty internet. Answer is yes, it's even number. Okay, sure. All right, I did bad on this one then. Let me go fix that up. Here's our practice midterm. So all of these then would be bolded here, right? So 1, 2, 3, and 4. First row, right? And then that's just 5 and 7 from the second row, and 2, 1, 2, 2 from the third row, right? So that's the one here. Does that make sense? What I was looking for with this, just navigating around using indexes, doing some silly things. I'm going to ask about prime values. That sort of, I'll give you a function if I ask about primes. Technically, it's neither even nor odd, Trumpet Man. Okay, well, the internet let me down then. BBC News? For mathematicians, the answer is easy. Well, sure. We'll go for it. Not. All right, so there's a question on the list, right? Having fun with those. And then we'll have a question on recursion. One question on recursion. Now, this one was actually a two-part question, which I thought was interesting, if that's all right. So you write a recursive function, and you write an iterative function. Right, so you have to do it both ways. Right, this is like a simple recursion with a loop, and we just replace the loop with that iterative function here. So it's the sum of all the ordinal values of the characters. Remember, you can get ordinal of a given character, how to get the value out. Okay, so that's 1 point each and 5 points each. Okay, so 30 points total. Right, so half of it's the quiz style, half is these long answer style questions. And then, of course, we have to change the font. Let's go with something a little more friendly here. Let's go with some Comic Sans. So there's the practice midterm for you folks, okay? So get the quizzes done, and I can get them graded for you. I graded a couple that were already in, and we can go from there, okay? Questions, thoughts, concerns? Whew. I gotta go lay down. Excuse me. All right, folks. It's been fun. We'll talk more about linked lists on Thursday and Project 1, the Recursion project. Let me know if you got any questions, and we go from there, okay? All right, thanks, everybody. See you around.